May I have your attention, please? The opening ceremony of the International Symposium on Biomedical Engineering 2020 will begin shortly. Please allow me to inform you of few rules to help make sure today's opening ceremony runs smoothly. Please make sure that you have adjusted your paper ID and full name in accordance with the name that you are currently using for your Zoom application account. We kindly request all guests and participants to please mute their Zoom account to prevent additional noise during the opening ceremony. At the end of the opening ceremony, we will have a photo session, so please make sure to turn on your camera for the photo session. I will inform you later on. Ladies and gentlemen, welcome to the virtual International Symposium on Biomedical Engineering 2020. This is a new era in our lives, the new normal era, where we interact virtually while maintaining the COVID-19 health protocol. This year's symposium will focus on empowering multidisciplinary partnership for healthcare product industry and services. Ladies and gentlemen, with the widespread pandemic of COVID-19, after a careful consideration and taking into account multiple precaution measures, the International Symposium on Biomedical Engineering 2020 committee has decided to change the symposium method from oral presentation to virtual or remote presentation by using Zoom application and video presentation. We would like to thank all of our keynote speakers and participants for making the time. Ladies and gentlemen, please welcome to the screen the General Chair of International Symposium of Biomedical Engineering 2020 Organizing Committee, Associate Professor Sugeng Supriyadi, to give his report.
Okay, thank you, Ms. Tika. Assalamualaikum warahmatullahi wabarakatuh. Dear Honorable Dean, Faculty of Engineering, Associate Professor Henry D.S. Budiono, Dear Honorable Dean of Faculty Kejuruteraan Mechanical Engineering, UITM, Prof. Muhammad Asmi Ayu, and the Honorable Director RCBE, Associate Professor Yudan Bulanza, Honorable Keynote Speaker today, Prof. Uda Hashim, Prof. Yehuda, Dr. Basari, Prof. Soleh, thank you for valuable time to share the current issue in biomedical engineering, especially now combating COVID-19. And also, honorable ISBE participant. As we know that ISBE is an annual program of Research Center Biomedical Engineering to gathering researchers on biomedical engineering field. And today, collaborative work from various disciplines will give the significant impact to realize research from design into product to give benefit to society. And this year is being held using online system due to the pandemic COVID-19. Hopefully, even using online system will not reduce quality of interaction and collaboration that will participant can interact each other. And especially the COVID-19 is a global challenge, so that we should solve across the nation, not only one nation, but collaborative. The online plenary and parallel session conducted using Zoom meeting, and if we need some special room for discussion, intensive discussion, we provide a breakout room for participant. And plenary session also can be accessed using YouTube channel of Faculty of Engineering, Universitas Indonesia. And in today plenary session, we bring to you 4 keynote speakers. Number 1 is Prof. Uda Hashim from University Malaysia Perlis. He will talk about the medical diagnostic device for COVID-19. And Dr. Basari, he will share experience from scratch into product of ventilator. Prof. Masafumi Yoda from the Tokyo University of Agriculture and Technology, Japan. Also, he will talk about the COVID, especially automated real-time PCR. And also, Prof. Solehuddin from University Technology Mara, Malaysia, will talk about the finite element model to application to be applied in industrial revolution. And I will report in here that our participant in here, there are 104 papers submitted to ISBE from Indonesia, from Malaysia, from Japan. And the conference topic cover parallel session is biomaterial, medical device, and drug delivery, and also special topic in COVID-19. And all selected paper of ISBE 2020 will be published in some journal, like International Journal of Technology is Q1, and Journal of Mechanical Engineering, Q3, Journal Tribology, Medical Journal Indonesia, and all submitted paper, all accepted paper will be published in AIP proceeding. Yeah. Then additional processing charge might be needed for this journal. And we will make the evaluation on the presentation by chair and co-chair during this session to decide who will promote into that journal. Finally, I would like to thanks to colleagues from UITM as a co-host of ISBE 2020. Hopefully from this conference we can get some benefit and also can make a strategic collaboration. Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Ladies and gentlemen, today's symposium will not be possible without the full support from the Faculty of Engineering, Universitas Indonesia. Please welcome to give his previously recorded opening remarks, the Dean of the Faculty of Engineering, Associate Professor Henry D.S. Budiono.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Honorable Director RCBE UI, Dr. Yudan. All keynote speakers consist of Dr. Basari from FTUI, Professor Uda Hashim from University Malaysia Perlis, Professor Masafumi Yoda from Tokyo University of Agricultural Technology, Professor Saleh Hudin from University Technology Mara, Malaysia, and distinguished Professor Ismail and Professor Muhammad Asmi. As I know, Professor Muhammad Asmi is Dean of Faculty of Mechanical Engineering UITM, and then Professor Ismail is Vice Dean for Research from University Teknologi Mara, Malaysia. And the last is Dr. Sugeng, Chairman of the ISBE Conference 2020. It is my great pleasure that I welcome all participants of the International Symposium on Biomedical Engineering, or ISBE 2020. The quest for knowledge has been from the beginning of time, but knowledge only becomes valuable when it is disseminated and realized to benefit humankind. This quote on transforming idea into reality has influenced the role of collaboration among multidisciplinary fields in the development of the nation. Faculty of Engineering, Universitas Indonesia established Research Center on Biomedical Engineering, or RCBE, in 2015. Currently, RCBE plays strategic role as an interface between science and medicine. Engineers and scientists are the backbones of technology development, and clinicians are key in the application of technology. Emerging engineering and medical field toward human is a very significant contribution to solving problems in society. Faculty of Engineering Universitas Indonesia has been contributed to fighting COVID-19. Faculty of Engineering Universitas Indonesia has developed and distributed several products such as movable hand washer 250 units, disinfectant chamber 75 units, Indonesian propolis for COVID, flock swab 100,000 units, swab chamber ventilator, and then ventilator Uicoven 300 units, and on progress high flow nasal cannula. It is envisaged that the intellectual discourse will result in the future collaboration among universities, research institutions, and industry, both locally and internationally, through ISBE 2020. In particular, it is expected that the focus will be given to issues on the development of biomedical engineering. It is hoped that ISBE 2020 will be a platform to gather and disseminate the latest knowledge in medical and engineering. Academicians, scientists, researchers, and practitioners of engineering will be able to share and discuss new findings and application of the current situation, especially global challenge on COVID-19. It is what we are today. Here we gather with old colleagues, academic peers, new friends to talk about old topics or brand new issues that we might know just today. This conference held during pandemic that forced us to use an online platform. Hopefully, this condition will motivate us more to make good progress in biomedical engineering. Today, in 5th ISBE, we will hear and hopefully be inspired by plenary session from Indonesia, Malaysia, and Japan that understand the cutting edge of current trend technology in biomedical engineering. Let us remember this will moment of united engineering, medical, and answering the challenges on biomaterial, medical device, drug delivery, and combating COVID-19. We have succeeded in establishing dialogue, as well as a network of bilateral and regional association agreement. I would like to thank our colleagues from University Technology Mara, Faculty of Mechanical Engineering, for their gracious support. Additionally, I extend a hearty thank you to the member of the organizing committee for dedicating their valuable time for preparing this conference. May have a successful, stimulating, fruitful, and rewarding conference. Billahi taufiq wal hidayah. Assalamualaikum warahmatullahi wabarakatuh.
Ladies and gentlemen, each year the International Symposium on Biomedical Engineering tries to expand our partnership by inviting other universities to join us to co-host our conference. This year, we are honored to have the opportunity to host this symposium with the Faculty Kejuruteraan Mekanikal, University Teknologi Mara, Malaysia. Please welcome to your screen, representing the University Teknologi Mara, the Deputy Dean of Research and Industrial Linkage, Faculty of Mechanical Engineering, University Teknologi Mara, Associate Professor Muhammad Hussein Ismail.
Assalamualaikum warahmatullahi taala wabarakatuh, and a very good morning. Selamat pagi, yang berbahagia, Prof. Sugeng, Chairman of the 5th International Symposium on Biomedical Engineering, Honorable Dean, Associate Professor, Prof. Henry, Dean of Faculty of Engineering, Universitas Indonesia, our distinguished speakers, the keynote speakers, Dr. Basari from Biomechanical Engineering, Universitas Indonesia, Prof. Uda Hashim from Institute of Nanoelectronic Engineering, Mas Fumi Yado from the Department of Biotech and Life Science from Tokyo University of Agriculture and Technology, and Associate Professor, Engineer Dr. Solihuddin Shoaib from the Faculty of Mechanical Engineering UITM. And ladies and gentlemen, first and foremost, I would like to congratulate to Universitas Indonesia, particularly Research Center of Biomechanical Engineering, for organizing this symposium, the 5th symposium of Biomechanical Engineering. And this year, we have been honored co-host with Universitas Indonesia in organizing this event. For information, in UITM, we have a center of excellence for the research on biomedical engineering under the Faculty of Mechanical Engineering. So this RIJ have been established in 2016. Of course, this is a new norm for us, not only Indonesia but also in Malaysia, in combating the pandemic COVID-19. Initially, it was planned by the organizing committee to organize the 5th International Conference of Biomedical Engineering in Bali. I got the opportunity to present papers during the 4th ISBE in Padang last year. And then for this year, it has been honored that UITM got opportunity to co-host with the Universitas Indonesia in this event. ISBE is an annual event initiated by the Research Center for Biomedical Engineering, Universitas Indonesia. And this event is organized in order to improve the communication of science, research and technology among students, faculty and researchers, not only from Indonesia, but students field of biomedical engineering. For this year, 2020 session, due to the pandemic COVID-19, this symposium is organized virtually, okay, and co-hosted by the research biomechanical engineering from UITM. And I would like to thanks to all the participants who are joining in this ISBE, particularly from Indonesia and all other countries. So of course, we are struggling against the pandemic of COVID-19. For this year, as what have been highlighted by Prof. Sugeng, our paper will be published in AIP conference proceeding, which is Corpus Index. Besides that, we also some of the papers will be selected for the international journals, such as journals owned by the Universitas Indonesia, Journal of Technology. And we also, in Malaysia, we also offering journals under the mechanical engineering, International Journal of Mechanical Engineering, JMechE, and also Journal Tribology. I would like to wish thank you very much for the opportunity given to us from the Universitas Indonesia for giving us opportunity to hope that platform for all the researchers to not only for presenting the new findings on biomechanical engineering, but it is hoped that this will be a platform for us to share the new knowledge on the current technology or the current research related to biomechanical and biomaterials engineering. The integrations of the engineering discipline and biomechanical engineering is very important in the current situation now, for example, in pandemics, because there are many entered by researchers due to this COVID-19. So the involvement of the researchers from the engineering faculties as well as from the medical faculty is very significant to give the impact to the society. So it is believed that we give an impact to the society. Okay. On that note, I wish the event a success, and hopefully it could inspire and benefit the whole university, particularly the organizing from Universitas Indonesia and co-host University Technology Mara. And I'd like to take this opportunity to offer my sincere appreciation to the of UI for making towards the success of this event. Okay, thank you very much.
Ladies and gentlemen, before we continue on with the first plenary session, we would like to invite all participants to take a few official photos together. I will help you in organizing the photo session today. So I would like to invite everyone who is currently setting your video to off to please turn on your video in your Zoom application for the photo session. Okay, everyone ready? So we have, in my laptop, there are 3 pages of participants. So I'm going to start with the first page. Everybody look at your camera and smile. 1, 2, 3. Okay, finish with the first one. And then we are moving on to the second page. Please turn on your camera for the photo session. Okay, everyone ready? 1, 2, 3. Okay, and then I'm going to move on to the last slide of the participants. Everyone, please turn on your camera, and we will take a picture. 1, 2, 3. Very well. That's it, and we have finished the photo session for today. Ladies and gentlemen, the opening ceremony of International Symposium of Biomedical Engineering 2020 has ended. We will now take a short break while we are preparing for the first plenary session. We kindly request that you stay with us for a few minutes and enjoy the following video that we have prepared for you. The video will tell the story of 7 research products developed by the Faculty of Engineering Universitas Indonesia in collaboration with several faculties within the university and other institutions in the fight against COVID-19.
yang Sulawesi A minus 79, sehingga kita berpikir, wah ini potensial sekali nih psikopolis ini untuk yang coronavirus yang baru ini.
Ladies and gentlemen, we will now begin the first plenary session of the International Symposium on Biomedical Engineering 2020. Before we begin the plenary session, please allow me to inform you of a few rules to help make the session run smoothly. Please make sure that you have adjusted your username into your paper ID and full name in accordance with the name and the paper ID in your registration. Please make sure that your microphone is set to mute during both the plenary sessions. If you need assistance during the session, please use the chat room to inform the organizing committee, the host or the co-host, if you need any assistance. Please use the raise hand button during the question and answer session. And if you are interested in further discussion with any of our keynote speakers, the committee has set up breakout rooms. Please contact the committee through the chat room for further assistance if you wish to join this breakout room. Ladies and gentlemen, our first plenary session will feature talks from Professor Uda bin Hashim from Institute of Nanoelectronic Engineering, University Malaysia Perlis, and Dr. Basari, Head of Biomedical Engineering Study Program, Faculty of Engineering, Universitas Indonesia, and also Head of Ventilator Team, Universitas Indonesia. The first plenary session will be moderated by Associate Professor Yudan Wulanza, Director of Research Center for Biomedical Engineering, Universitas Indonesia. Please allow me to read a brief profile of the moderator before I transfer the screen to him. Associate Professor Dr. Yudan Wulanza earned his bachelor degree in chemical engineering in 2000. After 2 years working in a company, he decided to study Master of Science at Aachen University, Germany, and started to join the Department of Mechanical Engineering, Universitas Indonesia in 2006. In September 2008, he pursued his PhD program in bioengineering at Piaggio Research Center, University of Pisa, Italy, as part of the European Union Asia Link program. He returned to Universitas Indonesia in January 2012 after the completion of his PhD program. Currently, he serves as the Director of Research Center for Biomedical Engineering, Universitas Indonesia. He has published more than 70 journals and proceedings, and his research interests are biomatics, biomaterials, biosensing, biomechanics, and locomotor tissue engineering. Dr. Yudan Wulanza, the session is now yours.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Thank you, Mystica, for beautiful entry for me. And so today we will have our valuable friends here that would like to speak on their specialty on the general topic will be about the medical devices. And our first speaker is Sim. So before we give time for our valuable Prof. Hasim, I would like to read of his CV. And Prof. Hasim is currently is a senior professor in University Malaysia Perlis, which has his bachelor and PhD from University of Kebangsaan Malaysia. Upon his graduations, he works for about 15 years and has a very vast experience and CMOS fabrications. And currently, he is the director of Institute of Nanoelectronic Engineering, 2008. And his research interest is mostly in nanotechnology that includes biosensor, DNA chips, microfluidics, nano lab-on chips for almost all very critical fields like medical, foods, agriculture applications. He has been well known in technology research. His high index is 39 with more than 7,000 citations from his more than 1,000 papers. So I'm very gladly today that we will have our Prof. Uda Hasim. So for in the next 20 minutes, I would like to present Prof. Uda Hasim for his presentations. So please, Prof. Uda Hasim, the time and floor is yours. Prof. Uda Hasim.
Okay. Assalamualaikum
please.
warahmatullahi taala wabarakatuh. Thank you, Dr. Yudan, okay, for your introduction about myself. Thank you very much. So first of all, thank you, Universitas Indonesia, for inviting me. It is my great honor to be as a keynote speaker in this conference. So this is my first debut in organized by Universitas Indonesia. So to make it short, so the title of my presentation is Medical Diagnostic Device for COVID-19 Detection. So it is a preliminary evaluation towards clinical trial. Okay. It is very much affected our current interest right now. What we are facing, the whole world are facing the same problem. So the keyword of my presentation basically is about nanotechnology. So every one of us aware about what is nanotechnology, and then biosensor, diagnostic system, and the like is a target sample, and the like. Our target sample here is a COVID-19 sequence, bioreceptor. So the probe that I'm using in this sensor is a single-strand COVID-19 RNA transducer, the device that convert the biological reaction into electrical signal, and then return into quantitative measurement. Microfluidic, the device that control the flow of the fluid. Lab on chip, we just miniaturize the actual lab into a very small lab on chip. Internet of Things. So it is something that we are talking now. It is on the communication. So everything are included in my product or in my solution. So we are also talking about rapid and labor-free. So everything must be rapid. We want something that show us a very fast result. Labor-free, we don't want to process the sample. We just took the sample and drop on our device and show the result. It's almost similar like a glucose meter. And then everything must be quantitative. Otherwise, we have to have expert to interpret all the data. So now we want to deliver our solution to the community. Must be very sensitive, must be very selective. Of course, what we are targeted is the accuracy must be 100%. So I will talk my presentation around this word. So this is about COVID-19. Okay. So my motivation comes up after this one become a very severe problem now to the whole world. We are facing a problem basically at the initial stage, basically on the diagnostic kit. Okay, very difficult to get the diagnostic kit with the high accuracy. So in Malaysia, we need something more than 85%. Then we can apply for the clinical trial. Okay, and then it's become very severe now. So the numbers increasing every day. The numbers of deaths, okay, the numbers of cases are increasing. So make it the whole world scared about this disease, which we can't see. Okay, we can't see, but we can see the effect. So this is the motivation basically. So in Malaysia, because of the proper control now, everything are reduced. The cases are reduced into single digit. We are under control. So the lockdown is already off. So now we can, but we have to follow the SOP, the protocol set by the Ministry of Health. Basically, in my research, what I did is to help the biotech people, scientists, to develop the drug by having the right diagnostic kit, okay, understanding the behavior characteristic of the disease, so they can design the right drug, the right vaccine, okay, to combat the disease, and also to help the doctors. If we can diagnose fast, so the doctor can act to the patient immediately. At the moment, for the kit that we have in the hospital, they require almost 1 day, 3 days, just to get the result from the patient. Okay. Of course, finally, we want to make people happy and healthy. So this is the current scenario about the diagnostic devices. Everything are lab-based. Okay, so we have to bring the sample to the lab, and everything are conducted in the lab. Require expertise to interpret the data. So this is another bottleneck also in the lab. We don't have enough expertise, expert to interpret the data. And then everything are done manual. Of course, human error we cannot avoid. Time consuming, as I mentioned earlier, label-based. They have to process the sample until they can recognize the sample. Finally, they go through the protocol just to confirm the target sample. Single detection will be done one by one. They cannot do in batches. And high volume, expensive, of course, PCR is very expensive equipment, high energy, less sensitive, and not specific. Sometimes different sequence also we can detect. Okay, so this is what the demand. It must be rapid, label-free, sensitive, selective, handheld. It's almost like a glucose meter, automatic data interpretation. They will show the result immediately based on quantitative, based on numbers, so that we can know the situation of our health in situ. Okay. And then for the diabetes patient, the problem is they are normally scared with the blood, with the needle. So this kind of situation also we have to come up and help them how to solve all these problems, especially the elders, okay, the youngest, they are very scared and phobia with the blood and needle. So my strategy in research with respect to this biomedical application, so I'm trying to push myself in research from invasive to non-invasive, okay? From using blood, finally using sweat. The only difference is basically the target disease, target sample in the urine, for example, is less as compared to the blood. It's very less in the saliva as compared to the urine, and of course very less from the blood. But it's almost close to zero or extremely less in the sweat as compared to the blood, urine, and saliva. The only thing in research what we need to do is to push ourselves to improve the sensitivity of the device. Okay, that's why the nanotechnology comes in. We have to make sure the device is really sensitive. Not only sensitive, must be ultra sensitive. This is our job actually in the engineering perspective. And then if you look to my direction, research direction, okay. So there are 3 components that I have to focus in. One is the sample, the other one is the sensor, The third one is the reader. So all these three must go in parallel. Okay, the sample, for example, normally we prepare in the lab. We have to push ourselves, go to the kit-based preparation, that finally lab on chip. Everything are prepared on chip. Okay, on chip. And then for the kit sensor, so at the moment, currently, most of us are using antibody binding. And then they improve the sensitivity. They are using, introducing aptamer, so that they also can observe the DNA, RNA. But they are still spectrophotometric. But now I'm using the DNA or RNA in my research, so that we can go to the very specific detection. And then they will be very, very sensitive. And then I also improve the lab, the reader, the measurement system, from analytical measurement in the lab, everything are lab-based, very bulky, very big system. And then I redesign everything, become electrical mechanical system, but still not that small. Okay, it's almost like as big as a computer. Okay, and then finally I redesign again and again. Finally comes up with a low noise electronic reader. It's a small gadget which can become a handheld for the detection. So this is my device actually for the diagnostic COVID-19 diagnostic device. Okay, comprising of three components. Okay, one is a reader. Okay, this is a reader. So this is a reader. This interface, and then this is a sensor, and then the third one is the smartphone for the IoT application. Okay, whereby the result will be transferred online. Okay, to those who are interested to know the result. Okay, so one machine, one device can transmit to as many as possible. Maybe the whole doctors, they want to know the result, so they can go through, just look at their screen of the smartphone. So the main component of this device basically is a sensor. The novelty part is a sensor, whereby I patent almost how many patents here? Two patents come from the sensor. So the novelty part is the sensor. So sensor, basically, this sensor basically comprising of two components. One is the actual sensor. Okay, so this is the actual sensor, the bare IDE, and then the functionalized IDE. And the other one is a microfluidic. This is a microfluidic. Okay, and then this is the complete lab on chip, whereby I already attached the sensor to the microfluidic and become a lab on chip. I drop a sample here, and then we go through to this 3 point of care, so that I can repeat simultaneously. Let's say do the first measurement, second measurement, give the same result, and then this maybe I can use as a reference. Okay, so this is the whole system that I did. So basically, to come up until this level, I took almost more than 10 years. I spent almost more than 5 years, 8 years on the sensor itself, until I come up with a sensor. Because when talking about sensor, the most important thing is about the sensitivity and the selectivity. People will ask about the sensitivity of a device, repeatability of the device. This is very, very important. I have to do a lot of research, okay, to come up with the data. Value proposition of my device. I compared with the conventional method technique in the lab currently. So my system only require about 30 minutes, actually about 15 to 20 minutes if the sample is already extracted. Okay, so this is what actually I requested from the hospital, from the lab, extracted sample, less dangerous to me. So extracted before they send to the PCR to enhance amplify the signal. So I took this one and then I just dropped to my device. And then within 10 to 15 minutes, I got the result. But for PCR, not less than 6-8 hours. Then when the result comes up. Okay. But normally for the positive sample, they took 3 days. Negative sample 1 day. And then the sensitivity is 1 femtomolar, whereby the current one is about 1, and then the latest is about 1 nanomolar. Okay. Mine is about 1 femtomolar, is almost equal to single molecule detection. The measurement method is a quantitative electrical signal label-free, whereby the conventional qualitative, they are still based on colorimetrics, still based on spectrophotometrics. And then label-based, they have to process the sample. The process flow are very simple, and then the process flow for the conventional are very complicated. and then not require any expertise, required expertise. So now I want to talk about the biosensor. What is biosensor? Biosensor basically comprising of two components. One is the bioreceptor, the other one is the transducer. Biorecognition element is a bioreceptor, and then the transducer. So the transducer, the job of the transducer basically is to convert all the biological reaction into electrical signal. Okay. So this bioreceptor comprising of two components here, the probe and also the linker. So in this situation, the probe normally is organic material, and then the transducer is the inorganic material. They have a problem at the interface. In the electrical perspective, they have a problem. They cannot attach together, they cannot communicate. So I have to design a linker so that they can communicate. So in here, I pattern my design. Okay. So I'm using this sequence for my probe. I took from the Ministry of Health. So this is the sequence that usually they use for the PCR. Come back to this DNA RNA principle. Okay. So RNA they exist in a single stranded, whereby DNA they exist in the double stranded. So what I'm trying to tell here is that so complementary, meaning that each and every pairs are meshed. So they are complement. Mismatch, some of them complement pair, and some of them are not meshed. Okay, mismatch. And then non-complement, all of them are not meshed. Okay. What I'm trying to say here is that if they are complement, according to the electrical perspective, from the physics point of view, so any two material, when they touch each other, they will introduce the electronic cloud. So the cloud is very, very small, very small. Okay, very small. We have to have a very sensitive device. So this is the device that I designed just to detect the electronic cloud. So I comes up with this principle after I do the modeling, numerical modeling. It shows that there's introduced electronic cloud. And then I start to design how to capture this electronic cloud. Because the cloud is very small, based on DNA complementary, based on DNA pairing. Okay, so if they complement, fully complement, so the cloud is a lot as compared to mismatch. So the cloud is less, whereby for the non-complement, so there is no cloud at all. Okay, meaning that electrically there is no current difference for the non-complement. We can see from my electrical measurement. So this one, how the probe target interaction. So everything I started with a transducer. Okay, transducer is a capacitant. Okay, it's a nano capacitant, and then I drop the linker. They call it, the process call it finalization, and then I introduce the probe, any specific probe according to the sequence. For this situation, I'm using COVID-19. That's why I'm preparing myself for future generation of the COVID. Could be COVID-20, could be COVID-21. So I have to have to work with the genomic expert or to come up with to me, so the right sequence. If they mutate from 19 to 2021, we have to prepare all those things. Otherwise, our vaccine that we develop are useless. Okay, so our vaccine are now targeting for COVID-19. It's not suitable for the COVID 2021. So we have to prepare ourselves so that we can follow the trend of these diseases. Okay, and then finally, so this one is so-called functionalization for this step, immobilization. And then, okay, I drop the sample. In the sample basically contain a lot of RNA, RNA X, RNA Y, RNA 1, 2, 3, 4, 5. But only RNA with a similar sequence only will match with the probe. In here, they will introduce the electronic cloud. If they are not similar, they won't complement, they don't give any electrical signal on the device. So the probe and they are almost like a magnet. Okay, if they are similar, they will go, because DNA, they are comprising of charge. Okay, negative charge. For the probe is a positive charge, so they will go and attach. if they are similar. So this is the step how to functionalize the device, comprising of 8 steps. You have to do it carefully so that they are repeatable, give the same result and so on. Okay. So this is in the graphic form. So this is what happened in the lab, what I'm doing in the lab. So I have to make sure they are really perfect. Okay. And then my device is very small. The device also very perfect, very accurate. So the size of the gap for the capacitance also must be repeatable. So this one have to be very careful before we start to functionalize the device. Okay. And then I start to measure at every stages. When I introduce any chemical on the device, I will do the measurement just to understand how they behave. Okay, I start with the bare IDE. So this is the result of bare IDE. Of course, they will give almost zero current. None of the electron are jump from one point to another point, because I'm supplying a very small current, nano M. Nano M is considered very small. I cannot supply a high, huge current because I supply, let's say, 100 nanometer. Okay, 1 micrometer, it will burn the DNA RNA. So we have to control it. Otherwise, that's why the current device cannot work with the DNA, because you will destroy and burn the sample. So I have to use a very small current. So to come up with this current value, I think I spent several years just to understand, okay, where the DNA RNA still survive, at what level of current value. Okay, and then I introduce the uptest, so that we get some different result here. We can see, so I measure at 1 volt. Of course, when I drop the probe, so the current value increase very significantly and then very smoothly, very nice. Okay, so this value I capture just to show that something is happening on my device after I introduce all this chemical. Okay, so this is the principle of the capacitance. If you are in the electrical, electronics, physics, you will understand the principle by using the equation of the capacitance. This thing will happen. Okay, so this for the probe value. So I obtain between 8.0 nanometer to 8.4 nanometer. So I'm using this value and then I coding in my system. So they will tell, so this is the value of the probe. So the value comes up after I repeated many times. Many master PhD student, undergraduate student doing the same thing, just to understand, okay, the properties of the device. And then this my reader, okay, it's electronic. Also some secret is there, because otherwise, because electronically there is a lot of noise. We have to cancel all the noise. So the best thing is we have to cancel the noise at the device level, not the system level. So comprising of amplifier, filter, voltage, screen, and so on. Everything are automatic. Okay, and also I include the IoT in this system based on the demand required by the doctors. So I include the IoT, whereby the result comes up on the screen, we transfer live to the smartphone. This is important, especially when the outbreak occurred. So they already said, when we do the measurement, if the result more than 30%, they will consider as an outbreak, and then the doctors, the team will come to the lab, understand the situation, and then they go to the site to investigate. So this is the importance of IoT. Same thing to the COVID-19. Normally they want to know from the central of, let's say, in Malaysia, Kuala Lumpur, in Jakarta. So if we have this device located in several places, so all the data will go to one central, and then they will get the right data, and then at the right time.
We have 5 minutes more, Prof. Uda.
How many more?
5 minutes.
5 minutes. Oh, okay. We try to finish it.
Thank you.
Fast. Okay. So this is the flow. Very simple flow. So if you look from this direction, so the raw sample, and then extract the RNA. Of course, they have to extract the RNA and then drop to my device, and then I can measure straight away. It's very simple. And then I can show the result on the screen of the device as well as on the phone. They will get a similar result. Okay, so now I want to show you the selectivity. Selectivity means if I drop a sample with target target DNA, target RNA. If without target, what is the result? So they give this, so this is the result, complementary, non-complementary. So this is a synthetic result. Just I want to validate my device. So I drop complementary, so meaning that, same sequence with the probe. So this is the result. Okay, very significant, very different result. And then you see here, the non-complement, they will fall almost similar with the probe value. That's very interesting. Okay, probe value. Okay, these are one example. Okay, and then this one for the sensitivity, I just want to check for this device, what is the smallest value they still can detect. So I reduce the volume, the concentration of my my target sample, the RNA. So I stop at 1 nanometer. This is because when I check at the lab, so the PCR, so the best one, they use the sensitivity is 1 nanometer. Basically, mine can go to until picomolar. Okay, picomolar. Okay, so it's very sensitive. You can see the different current different. Okay, it's very difficult to measure at nano amp, pico amp. Okay. So this one, okay, the validation, how I create the validation process. One, the first I validate my reader with the standard system machine, the Kitli, bought from US, and then I compare, okay, this on the system, and then after finish this one, this is very simple, and then I go to the sensor. First, I compare, I'm using a synthetic sample. Synthetic is a non-sample, synthetic I bought from Singapore. During the COVID time, I bought and then I test. Also give a very good result, and then followed by good sample. I just take a sample, this is good. Of course, the result is negative. I drop. And then, okay, the third one, good sample, and then I induce the virus. Of course, they will give a positive result. I want to see whether my device give positive or not. They give positive. Now I'm looking for non-clinical sample. These are real clinical sample. So I want to compare between mine with a gold standard, just to save a cost. So I want to use the sample, the clinical sample that stored at the lab. Finally, then we go to unknown clinical sample. We take the sample from the patient swab, and then we break it to two. One give to the gold standard, the other half give to me, and then I will go through. This example of the clinical trial that I did, and this one, I just put up a milk, curry, Nescafe, Tom Yum, Milo. So these are good sample. So they give, I think all of them are no. Okay. Okay, and then this the result comparing between Kitli and my device. They are almost identical, almost similar between Kitli and my electronic reader. This is what I'm trying to, I would like to show. And then this one, the testing and validation between my reader and the Kitli. Okay, so this is the result for Kitli, because in here I already set the turning point for yes or no. So the result, so this actually I want to understand, to validate my device. They give the same result with the Kitli. So what we can see is no. Here also they give the result no. Everything are very identical. There's a lot more. Okay, this analytical result, and then this result on the screen of the device. They are still identical. Okay, there's no error. So as a conclusion, so this device, in-house developed device, is 100% developed in-house in my lab. So it's ready to serve the community for this COVID-19 detection actually. So everything already functionalized, and all the fundamental data is already established. And then now I'm ready to go for the clinical trial, just to assist the ministry, government, to help them. Because my device, the measurement time is very less, because I'm comparing myself with the Cambridge. Cambridge, they claim 90 minutes. Mine is about 15 minutes. Okay. So this is what I'm trying to. I'm very happy now, waiting a response. So in here also in Malaysia, I'm giving a lecture to the frontliner, to the doctors nearby to my my university, and also in KL. I think last 2 weeks I give to in KL frontliner about mines. basically they are very keen and interested to have this one because they want to put at the airport. So when the people come in, we can measure them immediately, so can show that they can go back home if they are free of this COVID-19. So I think with that note, thank you very much for listening to my presentation. So thank you, Dr. Moderator.
Thank you very much, Prof. Huda Hasim. It's very nice presentations, and Masya Allah, it's we say luar biasa ya in bahasa. And okay, so I would like to direct to the Q&A questions. So although that we only have about 90 participants here, actually we also have YouTube streaming, and there are comments that are left there, and I would like to read questions, and I think, is it possible for you to answer all of this? I just
where is it? Where to have a look?
No. It's I already have in my cell phones, in my smartphone.
Okay.
So it's already it's already populated.
Okay.
First question is about the.
They can email me or they can WhatsApp me.
Oh no, it's already here. So I would like to read them. So the first one is how to fabricate such a transducer. That is the first one.
Okay.
The second one is what kind of linkers that you are using and how you are immobilize them in your sensor. And then the third one is, it seems that your sensor, your probe is capacitive. Is it limited only for capacitive readings? That is the third answer. Fourth is, do you also apply first before goes to the silicon oxides? And the fifth, so I only choose only five answers, five questions. And then the second one, the last one is there any specific mechanisms on coating the ammonia onto the silicon oxide? So I think that will be, please, could you address them if it is possible? Thank you, Prof. Huda Hasim.
So to make it short, I think I need to give a full presentation on the overall concept of these devices. So basically, okay, in my institute we have the complete facility for the fabrication. Okay, even we can fabricate the transistor. It's more complex than this one. So initially, okay, what I did is everything I've done in my lab just to understand the properties. So we have proper equipment to fabricate the device, can go down to nanostructure, there's no problem, just to understand the properties. If everything already fixed, so I will engage with the foundry to make it repeatable, to make it, more proper, because in research, of course, the repeatability is very difficult to control because the machine is normally used by many people, many researchers, so we cannot control the accuracy. So normally after I got the fundamental data, and then I will send to foundry to help me. So at this stage, because I'm talking with the private industry, private sector, if I'm to sell this solution to the businessman, so I have to engage with the foundry. So I already have the foundry in Malaysia, very close to me. Even they are my student as well. So I engage with them. I pay them and then they fabricate for me. Okay, about the linkages, as I mentioned earlier. So for the probe, there are several type of probe. We have to decide. There are amine, carboxylics, and also they have, and then the third one. So we have to decide on this one, and then only we have to design on the linker. We have to design the glue. What is the right glue? This is a chemistry. If we are in the chemistry, maybe we can understand. This is a chemistry. Just to link between one branch of the bond to another branch of the and then the link, just to avoid any linkages. So this one is very, very important. We don't want to have any leakage current, because the current we supply is very small. If they leak, we cannot measure anything. So we have to make sure they are properly linked. What else? Okay, so the device actually, I can use for any application, not only for COVID-19. It depends on the probe. Okay, what I need is a DNA or RNA sequence from the genomic expert or genetic expert, just to provide me, even to detect a cancer, even to detect any diseases, also can. And then I have to do some experiment work just to understand the value, and then I have to do some software to alter in my system as an algorithm. Then finish, we can start to do the clinical trial, the field trial. Okay.
Okay.
And then to know in detail, I think we have to have another session, inshallah.
Inshallah. And for last question, Prof. Huda, please address in only 1 minute. The question came from our colleague here in Faculty of Engineering, Dr. Arif. He was asking about how to control the sensor sensitivity. So it will be possible only sensing the COVID-19 virus.
Okay. So this because I'm using the COVID-19 probe.
I see.
It is not like because we are our understanding is about antigen antibody interaction. Because in the hospital they are talking about antigen antibody. I'm not talking about antigen antibody. I'm talking about RNA DNA interaction, probe target interaction. So they are based on the pair. So I will use RNA as a probe with a certain pair sequence, and then they will wait for their same sequence to be complement. They won't be miscommunication. No, they will communicate with the same species only.
I see. Thank you very much, Prof. Huda.
Thank you.
Yeah, we have very limited time, and maybe there will come another questions. Maybe you could answer in the chat room if it is possible. And however, I have to end your session. It is very beautiful.
Thank you very much.
I'm very grateful that you are here. We are having you here.
Okay.
I personally looking forward to having great collaborations with you and your university.
Inshallah.
By this, I will ask applause from the audience, and we should give thanks to Prof. Huda Hasim. So, Prof. Huda Hasim, thank you for your beautiful presentations and how addressing them.
Okay. Thank you.
Thank you, Prof. Huda Hasim.
Yeah, bye.
Bye. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullah.
Okay, we have very limited time, and I would like to go to a very good friend, Dr. Basari, to present his topics on low-cost ventilator COVID-20 for COVID-19. But before that, I would like to read his brief CV. So Dr. Basari is member ISBE, received bachelor degree in electrical engineering from Universitas Indonesia in 2002, and then continued with his master and PhD from Chiba University in 2008 and 2011 respectively. Currently, he has interest in areas of biomedical engineering from diagnosis, therapy, imaging, MRI systems, and antennas. And his publication is more than 150, including the proceedings and journals. And he is now just appointed as head of biomedical engineering programs for the Faculty of Engineering for undergraduate and master. So without further ado, I welcome Dr. Basari to join in the stage. So please, Dr. Basari, the time and the floor is yours.
Thank you very much, Dr. Yudan. I do hope that my voice is can be heard from.
Yes, perfect.
Okay.
Perfect.
Okay. First of all, we would like to thank you to be invited here as a keynote speaker, and it is an honor for me to present our research and experience about the ventilator. Assalamualaikum warahmatullahi wabarakatuh. Honorable guests in this meeting, ISBE 2020. I am Basari from Biomedical Engineering Universitas Indonesia. Would like to share about the ventilator that we have developed up to now. And today's title for presentation is low-cost ventilator called COVAN-20 for COVID-19 pandemic. I would share from the research and the production. Okay, first of all, would like to remind you, all of you may be already known about the biomedical engineering. There are a lot of application of the biomedical engineering. As we know that BME, Biomedical Engineering, has a logo, and there are several kinds of the word of biomedical engineering, like prosthetic, bionic arm, and then EEG, and data transfer by human being, and incubator, and a prosthetic or even DNA manipulation, and also imaging system. So there are a lot of biomedical engineering work, but basically what is the biomedical engineers is apply many of fields like electrical engineering, mechanical engineering, chemical, or even optical engineering, and other engineering principles or materials, etc. to understand, modify, or control biologic, especially for human and animal, or even sometimes it's a plant system, and also to design and manufacture products. The products should be should monitor physiologic function, or also assist in the diagnosis and treatment of the patient. So it can be diagnosis or treatment of the product, and also monitoring. So this is basically of the biomedical engineering. So this is very wide area of the biomedical engineering. Okay, directly I would like to share what's the motivation of our research, and the topic is, you have already known that because up to now, especially in Indonesia, there are two epicentrum of the spread of COVID-19, that is in Jakarta and Surabaya. You know, COVID-19 already spread over all of the province in Indonesia. 34 provinces have been infected, and the Jakarta and East Java now is epicenter of the spread. So based on the data yesterday, that more than 100,000 people are infected in Indonesia, and of them is about 4.8% is dead. So it's very sad that the spread of the COVID-19 getting higher and higher, like in this graph. So still increase. And there are a lot of necessity actually to tackle the COVID-19. So many researchers doing some research to tackle this COVID-19. As the previous presenter, speaker, is to develop the sensor detection for COVID-19 screening, and there are a lot of others of the tools for tackle this COVID-19. And one of the important thing or important tools in medical devices is ventilator. So I would like to share what the necessity ventilators in Indonesia, that because the COVID-19 in fact, it increased and increased. So it's predicted that about 30,000 units of the ventilators around Indonesia is needed now. And but unfortunately, that the availability of these tools is about no, maybe 9,000 units because this is of March. And surprising that still the health facilities centralized in Java, because Java is more than 60% of the population in Indonesia. And you know, each province in Indonesia, the ventilator availability is about 20 to 30%. So it's to very minimum of the ventilator availability. And I also would like to share about the facts in Indonesia that up to now there is no product from local, I mean Indonesia, to build the ventilator about the ventilator. So basically, ventilators needs in Indonesia is import tools, and 100% import tools. I have already checked in the e-catalog LKPP that there is no local ventilator originally made in Indonesia. So that's why this is motivate us to develop the ventilator. Oh, actually, this view is to make simple understand about the ventilator. The ventilator is defined as a machine. It's include in life support machine that serves to provide breath assistance mechanically to the patients at the patient or fully in effort to maintain oxygenation. So the key is maintain oxygenation or to improve oxygenation of the patients. So this video is, you know, this patient that need oxygenation, and this the ventilator can be transported to from one place to other place. Okay. Simply, types of ventilator is like in this slide that there are several ventilators, and the advanced one is called ICU ventilator, and this in the ICU room, intensive is care unit room. It's very expensive, this one. And the other types of the ventilator is called transport ventilator, emergency ventilator, and CPAP resuscitator. So in our research, we combine of this kind of the ventilator transport plus CPAP resuscitator in one tools. So this is our concern to develop the ventilator. And the ventilator is actually not developed only by Faculty of Engineering, but also in UI, because we collaborate with Faculty of Medicine, Universitas Indonesia. In this situation, we need to think about the low cost and can be transported ventilator, because it's needy to avoid a patient to going to ICU, because the ICU patients, basically the mortality rate is 80%, more than 80%. So it means if patient go to the ICU, the possibility to be dead is 80%. So it's very high. Why we choose transport ventilator? So because at least this is three reasons why we choose this one. That we look at the local spare part of the of this ventilator. That I think we think that there are a lot of availability of the local spare part if we develop the transport ventilator. And then because the infected people is less actually than the patient or people under surveillance, called PDP or ODP in Indonesian, in Bahasa. And even PDP or ODP sometimes experience shortness of breath. So that's why they need a ventilator to make oxygenation. And as I mentioned before, that we can set to CPAP, or I mean, this is what I will tell later, CPAP mode and CMP mode, to make one tools and affordable. This is why we choose the transport ventilator. And this slide describes COVEN 20. COVEN 20 is actually COVID Ventilator 2020 that we named to tackle the COVID-19. And this is a UI ventilator. Okay. There are several modes of ventilation actually, but we focus of at least two modes. This is called CMV or continuous mandatory ventilation, where the mode of ventilation is characterized by a ventilator that makes no patient effort to sense his or her breathing effort. So is triggered by the ventilator or time trigger. And the second mode is CPAP or continuous positive airway pressure, that we pressurize air is forced down to the airway to keep the airway open and free from obstruction, for basically for hypoxemic respiratory failure person or people or patient. And if we look at this, there are at least three of mode of ventilation: control, support, and combine. We choose the control and support it here because actually in the combined one in ICU ventilator. So we don't focus for ICU ventilator, but only for transport and emergency ventilator. Okay, if what is the standing of the COVEN 20 actually, because a lot of modes can be used in ventilator. What's kind of the developed modes in COVEN 20 is basically this like a diagram when doctor assess a patient, what is the priority? They want to comfort or they want to safety in hospital or not, or you can actually COVEN 20 can be used for volume control. CMV here can be considered as safety. You can go to this direction, or comfort as well, you can in this direction. And also we can COVEN 20 can be used for PAV or PSU support, pressure support ventilation. And so this standing of the COVEN 20 can be used in this kind of the mode for the patient. This is specification of COVEN 20 is actually anesthesia devices and therapeutic anesthesia. The mode, as mentioned before, there are two modes, CMV and CPAP, and this is actually in the specification for adults people, and there are also another for accessories. This is accessories, and the important thing is that in this specification is we use battery, lithium battery. So we don't use directly to AC cable. So basically the operation with the battery, so a small one, and this is the dimension, and the weight is less than 3.5 kilograms. This is the advantage of the COVEN 20. From this, I saw in this slide, the most important is cost effective, because our spare part is local and can be purchased in local market. So the cost is at least one third of the commercial product. Okay, how the ventilator works, this I would like to show the ventilator works diagram that from the oxygen tube and the oxygen from the installation in hospital can be used, and then regulated by regulator for pressure, and then can be mixed by mixer with the airflow from the outside, and detected with the pressure and flow sensor. And we use the control here, we develop a control here, and supply by battery, and can be charged in with a charger, and the result display in LCD display, and the gas flow delivered to the patient. This is a simple ventilator work diagram, and if any abnormal situation, there is a buzzer or alarm for this kind of ventilator. Okay, we have already patent of this property. There are at least 4 properties that we going to apply. That's first is patent and copyright. Patent already registered and copyright already, and the layout of the design integrated circuit like this we have also applied, and industrial design for industry partnership. And this is the proof of the application. And actually, our developed ventilator is transformed from one to other step. Yeah. First, we built the lab prototype 1, and then improve for lab prototype 2, and then the last is for industrial production. So now currently the prototype is product with industry is like this prototype. And we also test for product testing at Ministry of Health. It's called BPFK, Balai Pengamanan Fasilitas Kesehatan in Jakarta, and we did about 10 days for this product testing, for durability, for performance, and others. And we have the license. I mean the license from BPFK, so the product is passed, and then we make preclinical with the animal. Actually, this is the animal testing with the lungs of the pig, yeah? And this is our prototype, lab prototype 1. And then this is intubating directly to the lungs of the pig. We did with the IMERI FKUI, or Faculty of Medicine Universitas Indonesia, and quite good for the result. Okay, and then after that we did the clinical trials, because in this ventilator is class 2B, or in Indonesia it's class C, where the class C need clinical trials. And we did in the RCM in Jakarta, Rumah Sakit Universitas Indonesia, or UI Hospital, and then Persahabatan Hospital in Jakarta Timur, or East Jakarta. And these tools we use, and this is the documentation. And the result show that we did 2 modes, CMV and CPAP. For CMV mode, we compared the practitioner or medical practitioner, and also we did for ARDS. This is like a COVID patient. Like this, that it seemed that then the result is quite good for CMV mode. And also we did clinical result with the patient directly in RSCM, Cipto Mangunkusumo Hospital. This is the view of the clinical trial. And some patients, this is the criteria of the patient. There is inclusion and exclusion of the clinical trial. And the result of the clinical trials has been presented to the Ministry of the Health, and after that we got the license, the marketing license, 2 licenses here in 19 and 20 June of 2020. And the license basically is not us, but the industry. So this is the medical devices industry hold this license, but basically the product is from us. Okay. And then we are going to production by our partner, industry partner, and currently still going to 3 units of ventilator under production. Actually, about 150 already products, and we deliver to some hospital around Indonesia. And after that, we make a training directly in the hospital or even with the virtual training. And this is distribution area of the COVID-20 from Aceh to Papua. Now still, we have already delivered to Kalimantan, Borneo, and Sulawesi, and also Nusa Tenggara province. Now still going for distribution of the COVID-20. And this project actually, many of the partnership here from research and development from us, Faculty of Engineering and Faculty of Medicine, and also some hospital, and also Polytechnic Jakarta, Jakarta Polytechnic 2, and of course Research Center for Biomedical Engineering that I have been affiliated. And production, we have a partnership from the industry like the GTM Manager and Pindad, and also for the spare part we supported by Chemco in Jababeka industry, and others, Daruma and Petrosa. And because actually the scheme is fundraising and crowdfunding, so we also helped by alumni of the Universitas Indonesia. And this team actually not only in this slide, but actually many of the team that I cannot put in this slide. Okay, I would like to conclude in this presentation that COVID-20 has been developed as a transport emergency ventilator for COVID-19 pandemic, and COVID-19 already passed clinical trial and received marketing license from Ministry of Health, and then COVID-19 have been manufactured by medical device industry partner, and COVID-19 then delivered to hospitals in Indonesia. And actually this product, or this COVID-20, is realized as the pentahelix collaboration. Is maybe something new, pentahelix collaboration, sometimes triple helix, sometimes, but here academician, government, industry, and even society and mass media is collaborating this product. And thank you very much for your attention. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Barakallah, Dr. Basari, hearing directly from your sites it is very great, successful for your team that you are being able to accommodate all of the participants here, not only from the industrial, but also from the government and also the mass media. And that is indicated by the successful of the fundraising. Yeah. So I would like to read the questions from the YouTube channels. So there are two questions, Dr. Basari. The first one is questioning about what will be the real price, if that is possible to explore. And the second one is what is a specific reason that you are choosing using the pistons? Why using the pistons? And then come the third one is there any need for additional compressor to be able to generate high pressure airflow? So that will be total, total questions. So Dr. Basari, could you please address?
Okay, thank you very much for the question. And the first one is about the price, actually. You know, I have mentioned here, for example, this is the Hostech. Hostech is a product from China, yeah? And it is already entered to the LKPP, e-catalog, yeah, e-catalog Indonesian Ministry of Health catalog, and the price is about 50 million rupiah, 50 million rupiah. So this kind of the ventilator is, if we do for commercial, because now it's not commercial but still in the social entrepreneur or donation scheme. So in donation scheme we have 25 million rupiah. If we think about the commercial, I do hope that we can do like this Hostech commercial product from China, product that already exists in LKPP or less. Okay. We do hope that. That is the price, because we do not discuss yet about the commercialization, and I mean the price of commercialization. Okay, and the second is about the piston. Actually, our ventilator, actually we use a solenoid valve, so not a piston, maybe like a piston, but this is not a piston. This is like a valve. So many of the ventilator working principle is by valve. So if we just control the valve, solenoid valve here is on, off, I mean give the gas or stop the gas, something like that. And this is controlled by the control here, and the control is you know, like this. This is the control actually. This is the main board of the control. So it's very simple. And now actually in the next development is we want to minimize this one. So by touch screen, and then we just only few of the microcontroller to control the valve. So basically not the piston but the valve. Okay. And the last question, I forget. Can you repeat the question?
Do you need additional compressors to generate a high pressure airflow?
Oh, okay.
Is it a commercial one, or you do the own design?
Okay. We just need the oxygen. So compressor can be used, but the compressor, because the working of the ventilator is basically in the oxygen. So compressor is airflow. So there's only airflow.
Okay, I see.
To make pressure, you can use we use the flow regulator to higher or to reduce the pressure, basically like this.
I see. I think it will be sufficient.
Yeah.
And Basari, thank you for
Thank you
addressing
very much.
questions very well. And I believe there will be more questions that still coming. But however, we have to end the sessions. Okay. So I would like ask for the participants to give applause to Dr. Basari. Not could be hearing, but I think everyone feels how the spirit of the teams, and it could motivate the next products or the derivatives. So Dr. Basari, thank you for and that will be end these sessions. So in this moment, I would like to give my floor to the Mystica. Thank you very much. I would like to ending the sessions. Wassalamualaikum warahmatullahi wabarakatuh. Thanks for all presenter.
Very well, ladies and gentlemen, let's give a big round of applause for our keynote speakers and our moderators. If you could check on your Zoom application, on the reaction button, you can use clap for your reaction. Thank you very much. For all participants who have asked some questions, whether via our YouTube streaming or through the question and answer chat room, the committee is currently compiling all questions, and unanswered questions in the chat room or on our YouTube channel will be answered later on by the committee, so not to worry. And now, as we have previously announced, breakout rooms are available for further in-depth discussion with both of our keynote speakers from the first plenary session. Please contact the organizing committee through the chat room if you're interested in joining any of these rooms. And we will now take a short 5-minute break before we start the second plenary session, where we will play a video on the latest facility available at the Faculty of Engineering, Universitas Indonesia.
Masa toddler adalah langkah awal ia bereksplorasi. Inovasi baru Dental 1+ dengan Nutrisol diformulasi khusus untuk melindungi eksplorasi toddler Indonesia. Siapa yang iklan?
Hi.
Ladies and gentlemen, we will now begin the second plenary session of the International Symposium on Biomedical Engineering 2020. Before we begin the plenary session, please allow me to inform you and remind you again a few rules to help make the session run smoothly. Please make sure that you have changed your username by using the paper ID and your full name in accordance with the name given and paper ID given for registration. Please make sure that your microphone is set to mute during the plenary session.
No.
If you need assistance during the session, please use the chat room to inform the committee. Please use the raise hand button during the question and answer session, or just type your question in the chat room. If you are interested in further discussion with any of our keynote speakers, the committee has set up breakout rooms. Please contact the committee through the chat room for further assistance. Ladies and gentlemen, the second plenary session will feature talks from Professor Masafumi Yoda from Department of Biotechnology and Life Science, Tokyo University of Agriculture and Technology, Japan, and Associate Professor Solehuddin bin Shuib from Faculty of Mechanical Engineering, University Teknologi Mara, Malaysia. The second plenary session will be moderated by Associate Professor Muhammad Hussein Ismail from the University Teknologi Mara, Malaysia. Please allow me to read a brief profile of the moderator before I transfer the screen to him. Associate Professor Muhammad Hussein Ismail received his Master of Science degree in Mechanical and Materials Engineering from University Kebangsaan Malaysia in 2002, and also a PhD degree in Engineering Materials from Sheffield University, United Kingdom in 2013. He joined University Teknologi Mara, UITM, as a lecturer in 2001. Currently, he is the Deputy Dean of Research and Industrial Linkage of Faculty of Mechanical Engineering, University Teknologi Mara. His research interests are industrial metallurgy, materials, characterization, powder metallurgy, particularly metal injection molding, shape memory, and ITI alloy, porous biometallic or ceramics, and metallic foam. He has published 3 book chapters, 50 referred journals, more than 50 conference proceedings, both international and locally, 3 patents, and 1 utility innovation. Dr. Ismail, the session is now yours.
Thank you, Ms. Mystica, for the introduction. Now we are at the second session of the keynote presentation. Before we get started, just a little housekeeping. Please mute your microphone during the session. If you have any questions, type them. Let's begin with the first speaker for this second session. I'd like to introduce Prof. Prof. Masayumi Oda is a senior professor at Tokyo University of
Dia nggak bisa
Agriculture
di
and
screenshot lagi nih.
Technology.
Oke.
He received his bachelor,
Udah.
master, and doctor degree from the University of Tokyo. After research position at Central Research Center, Asahi Glass Co. Limited and Institute of Physical and Chemical Research, RIKEN, he joined the Department of Biotechnology of Agriculture and Technology as an associate professor in 1998. He became a professor at Tokyo University of Agriculture and Technology in 2003. In 2015 to 2019, he became assistant to president and vice dean of Institute of Global Innovation Research, Tokyo University of Agriculture and Technology. He has published in total over 240 journals articles. His research interest is biochemistry, molecular biology, biophysics, system engineering, and environmental science. So without further ado, I'd like to invite Prof. Masafumi Yoda.
Can you hear me? Can you hear me?
Yes, yes.
Okay. Oh, just wait a moment. Thank you very much for your kind introduction. It's my great honor to give a keynote lecture in ISBE. Okay, it doesn't work. Okay, I'm sorry. So, as you know, our world is suffering from a serious pandemic by COVID-19. By yesterday, more than 60 million confirmed cases and about 650,000 deaths have been reported. The numbers of contagion increasing. It causes serious problems around the world, not only in the healthcare, but also in economics. We have to unite to struggle against the pandemic. The fighting efforts to develop drugs and vaccines against the pathogen of COVID-19, SARS-CoV-2, are conducted in the world. However, it seems to require more time to be free from the spread of COVID-19 by the drug and vaccines. For the moment, we have to prevent the spread of pandemic by fighting infections. I have been collaborating with Japanese company, Precision Science, for more than 25 years. The company has developed an automated real-time PCR system, which has significant achievement in Europe and Japan. By introducing the system, I will introduce the recent progress in automation of the pathogen diagnosis. Just wait. This is my take-home message. Nucleic acid purification process is very important in the infection disease nucleic acid amplification test. It is rate limiting, and also it determines the accuracy and sensitivity. Infection disease tests are divided into two types: serological test and nucleic acid amplification test. Serological test is divided into antibody test and antigen test. So we call it nucleic acid amplification test, NAT. So there are many nucleic acid amplification methods. Among them, PCR is the gold standard. It is very sensitive, versatile, and robust. The only disadvantage is that it depends on thermal cycle, which requires a thermal cycle and also rate limiting. There are various isothermal amplification methods. Among them, I'd like to introduce LAMP and RPA. Loop-mediated isothermal amplification, LAMP, was developed by a Japanese company, Eiken. This is the amplification process of LAMP. It is very complicated. Using 6 primers and VST DNA polymerase from Bacillus thuringiensis, which has the strand displace activity, significantly large amplification is achieved in the isothermal condition. RPA, recombinant polymerase amplification, is the relatively new method. Similar to PCR, only 2 primers are used in this method. In addition to strand displacing polymerase, recombinase and single-strand DNA binding protein, SSB, are used in this method. Recombinase and SSB enable the primer binding in the isothermal conditions. These methods are have some advantage over the PCR, but I think PCR is better than the pathogen detection. This is the comparison of coronavirus detection methods. The advantage of real-time PCR is clearly shown. It can detect from only 1 copy of RNA. Compared with that method, the sensitivity of antigen test is significantly low. How the sensitivity makes the difference? Window period is defined as the average time from infection to detection. It is impossible to detect the pathogen just after the infection. It requires time for the pathogen proliferation. In case of HIV blood test, it takes about 5 days to be detected by...
Jadi 10 permainan dalam bahasa Sunda.
Pardon?
Main apa aja?
Pardon? What happened? Can you hear me?
Yes, please continue.
Oh, okay. So, antigen tests require about 20 days. There are a significant difference. Window period is the time required for the pathogen to proliferate to the detection limit. What determines the detection limit? In addition to the sensitivity of the method, amount of the sample is also related. Please consider the detection of HIV virus in the blood. In Japan, we take 400 milliliter blood for the transfusion. That test is performed to check the HIV infection. If the number of virus is 400 copies in it, the average number in 1 milliliter sample is 1. However, if the sample volume is 100 microliter, 0.1 milliliter, the average volume is 0.1, which makes the risk of false positive significantly high. Therefore, small sample volume increases the risk of false negative. This figure shows the case of transfusion-transmitted HIV infection in Japan. There have been some HIV infection cases caused by the false negative blood samples. These unfortunate cases are caused by the small volume test samples. That process consists of 3 steps: extraction and purification of nucleic acid from sample, amplification, and detection. In real-time PCR, detection is performed simultaneously at the amplification. This is the CDC protocol of SARS-CoV-2 detection. At first, RNA was extracted from the sample. 5 microliter of RNA was mixed with reaction master mix, and then thermal cycle reaction and detection were performed by the real-time PCR instrument. These are standard protocol for viral RNA extraction by the kits of the QIAGEN. Extracted the RNA was absorbed on the filter, and then washing and elution were performed by filtration or centrifuge. Compared with RNA extraction purification, real-time PCR is very simple. We have only to mix RNA and master mix and place the tubes in the instrument. Therefore, nucleic acid extraction purification is the rate limiting step for detection of pathogens. Of course, so as you know, we can skip nucleic acid extraction purification by direct PCR. However, there is some disadvantage. By direct PCR, we can avoid the process for nucleic acid extraction purification. In addition, sample loss does not occur in the process of extraction. However, application might be affected by the impurities and reagent. Sample amount is also reduced in the dilution. Therefore, generally, direct method gives relatively poor detection ability. Recently, microtust technologies have significantly advanced. Several microtust PCR instruments have been developed. Generally, microtust instrument gives sensitive and rapid detection from small volume samples. In these cases, thermal cycles occurs by passing through the preheated places. Thus, the time required for the temperature change of the tube is not required. It reduces the time for the application. Let's skip this one. However, it also had a problem in sensitivity due to small volume samples. Therefore, we have to be careful in applying microtust PCR for detection of pathogens. The process for nucleic acid extraction consists lysis of pathogens, absorption of nucleic acid, wash out impurities, and elution of the nucleic acid. As I talked, extraction and purification process requires centrifuge for filtration. Generally, it is difficult to automate centrifuge and filtration. In addition, we have to minimize the risk of cross-contamination. Magnetic separation was regarded as the primary method for automation of genetic analysis. Nucleic acid are absorbed or immobilized on the magnetic particles and collected by magnet. About 25 years ago, I have developed an automated robot system for genetic analysis. It is equipped with the pipettes, reagent storage, microtiter plate transfer system, and PCR. So this system can automate almost all process of the DNA analysis. We have also developed the magnetic separation system tool in it. Magnetic particles are collected by closing the magnet to the bottom plate. The collected magnet particle can be resuspended by pipetting with the removal of magnet. However, magnetic separation by this method is not easy. Moreover, resuspension process seems to cause cross-contamination. The problem is solved by magnetization technology developed by Pressure System Science. The system uses this kind of tips for the dispensers. The magnetic particles are collected on the inner surface of the tip by closing a magnet to the tip. The beads are easily resuspended by tightening with the removal of the magnet from the tip. Since all magnet separation procedure is conducted in the tip, the risk of cross-contamination among the sample is reduced. Nucleic acid pressure system using magnetization system technology has been solved by various companies, including Roche and QIAGEN. This is a procedure for nucleic acid extraction purification by magnetization technology. I will show video how it works. Okay. Thank you. And this is a present commercial nucleic acid pressure system using magnetization technology. So reagents are supplied at the cartridge. So we have only to place the cartridge in the system. So using this cartridge, we can perform extraction of DNA and RNA from their samples. And from 200 to 400 microliter samples, nucleic acid eluted in 50 to 200 microliter liters. It takes about 25 to 40 minutes. So automation minimizes manual labor and provide more reproducible result, possibly also higher quality. Automation is also necessary for scale up the pathogenic diagnosis. Moreover, it is also necessary for protecting inspectors from infection by the samples. So since the magnetization system uses only a pipette tool with a magnet, it is easy to expand for a fully automated system. Based on magnetization technology, PSS has developed a fully automated real-time PCR system, GeneLead. GeneLead is fully automated, sample to result, precision instrument. Samples, reagent, and consumer and placed in the instrument, and the assay is studied only by putting the button. Nucleic acid obtained from the sample using matrix technology. Upon completion, the nucleic acid transferred to the PCR well, and the PCR master mix was added, and real-time PCR thermocycle study. This is the inside stage of the GeneLead 8-channel system. Similar to nucleic acid purification system, the pipette with magnet separator moves one direction. PCR reagent and tubes are also supplied as cartridge. Full automated real-time PCR was achieved by very simple system. The fluorescence is monitored by the novel L/L scanner. The scanner is very small, so it's compatible with the conventional multiple PCR and the general real-time PCR systems. The light is excitation light and emission light. It goes through the optical fibers. So we can detect up to 6 colors for 12 samples in a few seconds. So let's see how it works by video.
Prof. Yoda. Prof. Yoda. Prof. Yoda, do you have 5 minutes left?
Okay, let's save time. Okay. Oh, no. Okay. So we have another one, Gene Lead 12 Plus. It has the 12 channel system and with pipetting tool for reagent dispensing. Gene Lead Plus is sold at the Elite Engineers in Europe from the Elitech company. It was used for various applications, including transplant pathogen monitoring, healthcare-associated infections, antibiotic resistant testing. The potential of the Gene Lead system was widely realized in the detection of SARS-CoV-2 detection in Europe. It was widely used in Italy and France. Gene Lead system has various advantages. It can automate all process of real-time PCR from sample to analysis. It gives high sensitivity and reproducibility. The analysis time is moderate, approximately 2 hours. Using 6-color detection, simultaneous analysis is possible. It can minimize the contamination risk. The system can easily adapt to novel pathogen by only changing primers. The problem is simple. The throughput is limited. PCR time is limiting, and also the sample number is not large. So to overcome this problem, so we have started to modify the system for the COVID-19 pandemic, and also for the future threats of the other viruses. To increase the number of the samples, we are building 24 and 96 channel systems, Gene Lead 24 and 96. By optimizing protocols, we will reduce the time for the analysis. To use our system in various areas, the supply of storage of reagent causes a problem. Generally, PCR reagent must be kept in a freezer. Therefore, we are trying to lyophilize reagents, which don't require freezer. Gene Lead is an ideal instrument for the bedside diagnosis. It enables bedside diagnosis in a small hospital. I hope to make our system will be used in Indonesia soon. Let's unite for the fight against COVID-19. Thank you very much for your kind attention.
Thank you very much, Prof. Masarumi Yoda, for the presentation. Is there any question from the floors? You can leave your question at the chat box.
Chat box? Wait. Chat. Oh, wait. I can see. Do you have any questions?
All right. Right, since that there's no question from the participants, thanks again to Prof. Masafumi Yoda for your presentations. Let's give a big round of applause to Prof. Yoda by clicking.
Thank you very much.
Yeah, for the clipping. Right. Thank you, Prof. Next, our second speaker for the second sessions of the keynote presentation, I would like to introduce Associate Professor, IRTS, Dr. Salahuddin Shoaib. Professor Salahuddin Shoaib is an Associate Professor of Mechanical Engineering at the University Technology Mara, UITM. He holds a Bachelor of Science in Mechanical Engineering from the University of Alabama, Birmingham, USA. Master of Science in Mechanical Engineering from University of Toledo, Ohio, USA. And PhD in Biomedical Engineering from University Putra, Malaysia. Currently, he is the head of Center for Postgraduate Studies, Faculty of Mechanical Engineering, University Technology Mara. His specific research interests are computer-aided modeling, optimizations, and simulation with applications to biomedical engineering, bio-inspired wing, and medical devices design. He has more than 50 journal articles, 80 proceedings, and 10 book chapters, and has been an invited speaker on numerous occasions at academic institutions throughout the world and national and international conferences. So I would like to welcome Associate Professor Dr. Salahuddin Shoaib for his presentation.
Assalamualaikum. By the way, Prof. Hussein, I cannot share the screen because the host disabled participant screen sharing.
Share screen, right?
Maybe the host enable me to share the screen.
Can someone help us on this?
Okay, now I can share. Okay.
Okay.
Now I can.
Right.
They allow already.
All right.
Okay. Okay. Can you hear me, Dr. Hussein?
Yeah.
Okay. Assalamualaikum warahmatullahi wabarakatuh. Bismillahirrahmanirrahim. Alhamdulillah wassalatu wassalamu ala Rasulillah. Okay, thank you for ISBE for inviting me to be a keynote speaker for this prestigious symposium. Congratulations for the committee because you have successfully organized a very successful program. Hopefully the conference that been organized can give a lot of insight to the researcher and new researcher to pursue their research work now and in the near future. So basically, the topic that I'm sharing today would be the current trend of modeling of the implant in biomechanics in the era of Industrial Revolution 4.0. Basically, I've been doing this research for I think nearly 20 years. Okay, starting from modeling, do a mathematical model, and then write a computer program, the algorithm for bone resorption, and also after that we, moved from a design analysis, and then we'll proceed to do the prototype by having the new or the latest technology. We have the technology of additive manufacturing that are booming nowadays. So that kind of technology really help the implant, especially the patient-based implant, to be ready to the patient. So as been introduced by our chairperson just now, thank you for very kind introduction. Basically, we have a center called Biomedical and Clinical Engineering Research Group at UITM. We have a number of researchers comprised of associate professors from different background in material, in applied mechanics, and also from Faculty of Medicine. So this is an outline of what I'm presenting today. I'm going to share a bit on the CAD and finite element analysis, okay, and then how to incorporate design for additive manufacturing in the design before we do the analysis, and then we also need to do the optimization, which is topology optimization into the analysis, and then we can produce it, okay, using additive manufacturing, 3D printing. And then after that, I'm going to share a bit about our previous, my previous work, what I have done for the last 15 years, and then what are the, what are the future trend that we can do to, if other new researcher want to pursue in this area. Okay. This is our research grant that we obtained for the last 5 years. It's a bit difficult now just to have a research grant. But inshallah, has been mentioned by our collaborator from UI earlier. Inshallah, we are trying to have more collaboration in this region and also in other regions, for example, in Japan or all over the world, so that we can, make this kind of research impactful. Basically, this is the niche of our research area, research group. We develop a new design of medical support and do also synthesis and processing, fabrication, machining, testing, and modeling of engineering material and medical support, and we do integration of engineering design and potential medical application, and also knowledge and technology transfer, and then we patent our design and our work, so that our invention can be protected. A bit on solid modeling and finite element analysis. I will focus mainly on the biomechanics and bone metal implant. If you look at this cycle, this is a schematic of the overall procedure for development of a medical implant. It can be hip implant, it can be knee implant, it can be tibia or whatnot. Okay, starting with the first one, we have here starting with the clinical evaluation. Okay, and then we have data collection there. From data collection, we can get it from CT scan in the form of DICOM file, and then from there we have can do a data transformation. Okay, data transformation. And in this part, we do the segmentation of data. Okay, data DICOM. DICOM we convert into STL file. Okay, this STL file can be used to do the straight away to do the printing by using 3D printer to produce by using rapid prototyping. Okay, and then step number 4 is design and customization. Okay, in this stage we have design requirement, okay, for the implant, and then next one is finite element analysis. Okay, we do the simulation. Okay, to see what will be the displacement and the stress, the strength of it, and then number 6 is design optimization. Okay, for design optimization, as mentioned just now, we can use topology optimization. This is a structural optimization. It can be also be a material optimization. Okay, so the commercially available software that can use this kind of optimization, there are Abacus and also NCs can do this kind of optimization, and then implant prototyping. Okay, and we can do the design improvement. Okay, analysis, discussion with a medical team, get their feedback. Okay, do the adjustment, and then the cycle will go, for improvement again and again. For geometric modeling, the model we can construct using in the preprocessor. We have different kind of software that are available in the market, and then the geometric model we can construct also in other CAD software. Then we import as STL file or IGS file, step file, okay, parasolic, etc. into preprocessor. Okay, and also the example of commercially available CAD system that's available. We have CATIA, ProE, SolidWorks, IBS, and AutoCAD. Just now I have mentioned, because right now we are dealing with the additive manufacturing. That's why when we start do the design, we need to consider or to plan our design from early on. That's why we need to look at the step, what we call a step in design for additive manufacturing. Okay, starting from the design concept, draft assembly of the concept, and then we determine candidate in the assembly, that could be eliminated. Okay, and then we determine if the new design concept is suitable, and then we develop new design alternative. Okay, with the reduced assembly, and then we determine the function and characteristic that could be optimized, and the optimization of the function, and then optimization of the characteristic, and then we select material for the parts in the reduced assembly. Okay, here is the process for design for additive manufacturing, starting from choosing the component of additive manufacturing. You can define design problem, define material, and then this is what we call the design automation of it, where we have the creation of initial design, we interpret of initial design to parametric CAD, and then we have all of this process, and then we can manufacturing and the process of post-processing. So what will be the way forward? Okay, the way forward for the FAM that I would like to share here is to develop a method for transformation. Okay, developing a method for transformation for an initial design into a parametric CAD model. Okay, and then another one is automatic coupling. Okay, automatic coupling of different additive manufacturing specific simulation model and tools. Okay, and then the third one is how to formulate an MDO, which is a multidisciplinary design optimization with specification of the most suitable objective and how constraints should be formulated and handled to get an optimal overall optimal design. Another thing that I would like to touch also over here is the aspect of for the last 40 years, okay, in this biomedical field, what most of the researchers they have done, and it has been summarized for the last 40 years. Before that, just to recap what we have learned, and these are steps in finite element modeling. We have the analysis of the model, okay, solver, and analysis of results. For analysis of model, we need to have a geometry of it. We have element and need to know the loading part of it, and then need to put a constraint, and then we need to know also the material and the properties of it. Okay, and then we have solver, and for the analysis of result, we can get the result in terms of displacement, stress, forces, and strain. And then all of the result we can plot in quantum plot, okay, XY plot, or in this thing. And this is the structure of a system. We have a preprocessor, solver, and post-processor. So as I mentioned just now, for preprocessor, we have geometric modeling, meshing, properties, loading, and constraint. And then for the solver, we have solving and the optimization, and then we can view the result. Okay. Okay. For the last 40 years, currently what's available for FE modeling technique, most researchers, they develop a representative model with appropriate loading and boundary condition. They also do the simulation of initial mechanical environment of bone implant construct, and they also do time-dependent adaptive modeling technique and design for computer-based experiment. And then they also look at the criteria for assessing the performance of joint replacement, and they do validation and verification. And for the last 40 years also, there are few challenges that being faced and we are facing right now. One of it is the material properties. Okay, and then also the fundamental, how to understand the behavior of the system and the physical process. Okay, and the third one is the study design. So the way forward, what we can do, it is suggested here, if you are interested to do, this kind of research, maybe the way forward is we can ask how to improve the sensitivity of the available modeling tools. Okay, we're talking about to improve their sensitivity. So the sensitivity of the modeling tool, we can improve in the study design through implementation of a statistical method. Okay, we can use probabilistic analysis. Okay, we can vary patient variability, and then also implant positioning, and also we can look also at computer assisted and robotic assisted surgery. Okay, we can capture information about patient, can plan the plan or the final position of the prosthetic component. And we also need to have what we call the understanding the behavior of the total joint replacement. Okay, and do decision support tool for planning orthopedic surgery. Okay, design the implant, design itself is one part, but another thing is the support system of it. We need to think about the complete system of it. Okay, that's the solution. Another thing I would like to highlight here, because just now we talked about optimization. Basically, I have done this kind of research back in 2016, because at that time we don't have the technology how to produce the implant that been optimized to produce it by using metal 3D printing. Because at that time, I think that technology is not available yet as nowadays, because right now we have that technology and the cost also is not that expensive. So as a brief background about the technique of the optimization, this is what we call topology optimization method. Okay, if you look at the procedure in topology optimization, starting with looking at the initial domain of it, we apply force, and then with the domains being discretized, and we have the topology of the domain is obtained and then being interpreted, and then we verify it. Okay, so by definition, so this method basically solve optimization problem. Okay, through distributing a given amount of material freely in the design space, so that performance is optimized. Okay. So looking at the process over here, starting with we define the design domain, we discretize, put load, and then we apply the topology optimization. We have the optimum topology, we have shape refinement, and then we do the solid modeling, and then we do the analysis. Okay, this is the case study that I have done last time. We assigned the material property of it. Okay, the cement and cortical bone, I assigned the elastic modulus of it for each part, and then have a Poisson ratio. Okay, this is what we call the design domain of it. And then this is a mesh domain and applied boundary condition. We have a head load and an abductor load. This is a very simplified one, just to see how we can apply the topology optimization. Okay, and then next one, I put the boundary condition of it. Okay, we have applied load case for for stair climbing and walking. Okay, and then these are the mathematical formulation behind. Okay, we have the design variable. Okay, and put the density for each varies. And what we did is we look at the reduction of volume. The volume we set to be 30%, 40%, 50%, and up to 70% from the initial implant volume. Okay, and this is the result, okay, of having a topology optimization. They can look at from 30%, 40%, up to 70% and how those three parts have been optimized by using topology optimization. And after that, we have a boundary smoothing, which is shape refinement. Okay, these five different topologies we obtain from one of the optimal implant, and then we interpret. Okay, we do the shape refinement of it. Okay, this is the solid modeling of the optimum implant. Okay, by using this technique, and these are the analysis. I don't want to talk very detail about this. You can refer to my paper that I have published quite some time ago. Okay, this one is the one that been printed by Altair website. Okay, they have printed this one, the bone and the perforated bone, and with the implant. This is the bone, okay, perforated bone, and this is the implant. They have printed it by using 3D printing technology. Next one, I would like to share, our ongoing project. Since 2019, what we did basically right now is for the last 5 years, what I did, we do the project of high flexion implant, high flexion implant, because most of the patients who underwent the total knee replacement, they can no longer flex their knee, cannot perform prayer, or cannot lap their leg. Before people in Asia or in Japan, we sit down, we do lapping, we lap, and then we perform prayer for a Muslim, so they cannot perform as usual. So the challenge is how to design the high flexion knee so that can be used to population in our area. This is our team member comprised of the orthopedic surgeon and manufacturing scientists and also the material scientists. We also have the industrial collaborator, okay, who specialize in 3D printing technology. Okay, and we have an MOU with this company as well. Okay, so this is the problem statement of of my project. What we are trying to do, because we know that the implant, there are the three main components over there. We have the femoral part here. This is the tibial part, and this is what we call a tibial insert. This is patella cap. So the challenge over here is we want to design and fabricate a high flexion total knee replacement. Okay, and then to test and evaluate the performance of the fabricated high flexion PKI. So the analysis and the mathematical part, that one have been done earlier. Okay, so this for this project we focus on to do to improve the design, final design, and to fabricate, and then do testing. This is what I mean by high flexion. We have here, this is tibial component. This is PE component. We call it tibial insert. This is femoral component. What I mean by high flexion is our knee. We started from here is 0, and then 45, 90, 165. So we would like to flex is more than 155 or more. Okay. Okay, this is the process of to do the printing and load object, arrange, set, printing, setting, preview, printing profile. Okay, this is our first set of the knee implant with these three components that being produced. Okay, we have produced it, and then right now been tested. We have sent to the lab in Germany. Also, I would like to share about the previous work that been done from 2009 to 2012. Basically, I developed what we call the bone resorption model, because we know that the bone implant and the cement. I'm talking about hip implant, cemented hip implant, because the challenge is one of the big challenges is loosening. Okay, loosening. So what we did at that time is we would like to have what we call to develop the algorithm, what we call the algorithm for resorption model. Okay, resorption model. And then from there we can do the lab prediction, okay, of the cement mantle based upon different kind of activities, okay. Because most of the analysis at that time they didn't consider the bone resorption. And also maybe for the future work, maybe the material scientists, they can think of how the material, for example, the cement can expand, or smart material, it can expand when the bone start to lose, okay. If the bone resorb by 2 micron, and the material, which is the cement or any smart material, it can expand 2 micron also, so that the implant can stay intact. This is another project that I've been doing. This project worth nearly 1 million ringgit. Is a multidisciplinary project, okay, involve many scientists all over the nation. We have the collaborator from, this is headed by Prof. Zainal. He is a professor in dentistry. It's headed by him. So he divided into different group to solve this kind of project, biomodeling of cranial maxillofacial reconstruction, patient specific. Okay, so basically we have 4 main projects at that time. First part is to do biomodeling. Okay, so we involve many mathematicians. Okay, because we don't want to rely on the available software in the market because it's very expensive. So we engage. We have open source, engage with many programmer and mathematician to engage in this project. And second part is a material scientist. We have the project of the synthesis of new PMMA HA nano composite for implant and prosthesis. And the third one is project rehab for patient with craniomaxillofacial defect. This is what I'm trying to stress. It is a combination of multidisciplinary project in individual. And then, we have what we call a patient-specific implant for additive manufacturing. Okay, these are the part that have been produced and put to the patient. Okay, so in conclusion, what I'm going to, the lesson learned from past experience and what we're having now, what I can say here is our project, which is related to biomechanics and implant. We need to have a dedicated multidisciplinary team. It is very important. Okay, what we call in our saying, cannot be hangat-hangat tiap ayam. We stop. We do just for the sake of publishing, something like that. But we need to think of the solution so that our people in this region can benefit. And then another challenges, okay, when bringing additive manufacturing to production, the main challenge is the process validation. I have attended additive manufacturing conference organized by ASME or last month. They also raised up the same issue. The main challenge, okay, when bringing additive manufacturing to production is the process of validation. So hopefully, inshallah, we can make use of the technology fully. Thank you from me. I give back the mic to the chairman, Prof. Ismail.
Thanks, Prof. Salahuddin Shoaib, for the presentations on the multidisciplinary research between the engineers, material scientists, and also from the medical doctors. Okay, the idea is to get the implant according to the certifications, right? So now we open question to the floors. If you have any questions, you can raise your hand through the reactions, or you can leave your questions through the chat box. Okay, there's 2 questions here. Dr. Salahuddin, Prof. Salahuddin. They use titanium for 3D prototyping. What is the challenge for using titanium? It is the first question from Dr. Sugeng Supriyandi.
Oh, yeah. Yes, we are using titanium. And we are using.
So what is the challenge performing the AM? Yeah,
it's very expensive cost. We have to do it very carefully. Okay, and then the machine that we're using is Renishaw Ren Additive Manufacturing 500E, and the printing hours is 8 hours, not including the cooling part.
Yeah.
Need to
so
have
the total hours will be within how many hours?
8 hours. 8 hours, excluding
8 hours
cooling.
just the process. Including cooling, yeah.
Excluding cooling.
Excluding.
Yeah.
Right.
Time consuming, and then need to have the expertise. Need to get. You cannot do on your own.
Okay. The second question is for the second question from Mr. Radi Malazi. I want to ask you about how do you modeling the bone material properties of healthy bone and osteoporotic bone condition in finite element method?
That one is very good question. Okay, for healthy bone, of course, very easy, and because we need to know first of all what type of do the main assumption first, which is isotropic. So we know the value of it. You start with the easiest one, which is the cortical bone of it. Okay, and we also need to know what will be the property for the internal bone, which is the internal part of the bone, which is cancellous bone. So we also need to have the property of it. Okay. So in finite element, the main thing is the value that we are using for E value. Okay, whether it is isotropic or orthotropic. Okay. I have published one paper related to that problem. You can refer to my paper back in 2012. Okay, in talking about considering the internal bone and external cortical and cancellous, and then what will be the stress involved inside that. Yes, Dr. Hussein.
Right. Is there any other questions? Prof. Soleh, just one short question. Is it possible to design the porous structure using the FEM? So meaning that for the cancellous bone and the different type of the bone, then we can design the different
porous structure.
Yeah.
Porous structure. The main thing is the design.
Yeah.
The design. People, if you look at the one that being printed by Altair just now, it shows you the perforated bone. Yeah, the perforated bone.
Okay.
Can be done. That can be done.
Right. I think there's no more question from the participant. Again, I would like to thanks to Associate Professor Dr. Salahuddin Shuaib and also to the keynote presentation, and look forward for the future collaboration with the speakers that had just presented just now, okay, on the specific topics. So I'd like to pass the floor to chairman of this ISBE, Miss Mystica.
Thank you, Dr. Ismail. Everyone, I would like to invite you once again to click the clap button on the reaction to give thank you to both our moderator and also our keynote speakers, Professor Masafumi Yoda and Associate Professor Solehuddin bin Shoaib. Thank you very much for taking the time to share with us your knowledge and also your research so far. As we have previously announced, breakout rooms are available for further in-depth discussion with both of our keynote speakers from both the first and second plenary session. So all participants, if you need to have further discussion, please contact the committee through the chat room. We will now take an hour break for lunch and also afternoon prayers before we start the parallel session. Before we do, please allow me to bring several information for your attention. The parallel session will begin after the lunch break and will be held in 3 separate Zoom meeting rooms. For those joining for room 2 on biomaterials and medical devices, yes, that's right, group 2 for COVID-19 and drug development and delivery, please stay in this Zoom chat room. We will not be moving to another room. However, for participants who are joining the biomaterials or the medical devices room, the links to these rooms are available on our website and will be displayed in the chat room information by the administrator team later on. We would also advise you to consult the parallel session schedule that can also be found on our website to see your schedule for the presentation and also maybe someone else's presentation that you are interested in checking out. The participant certificate will be distributed after the conference via your EasyChair account. The organizing committee will also send out an email to inform you when the certificate is ready. The committee will also select best papers, and the award for best paper will be presented at the closing ceremony tomorrow. We strongly urge and invite all of you to join us once more during the closing ceremony to celebrate the winners of the best papers. So, ladies and gentlemen, this is the end of the keynote session. Thank you very much for your attention and your participation. I wish you a good symposia and may you enjoy the parallel sessions today and tomorrow. Good afternoon, take care, and goodbye.